Yeah, g'day and welcome back to my channel. I've been working on updating this beautiful old Schaublin 125 CNC lathe with a modern Linux CNC controller. And this week it's time to get the saddle and some of this motion hardware installed, maybe even get something tested. But before I start lifting up heavy parts like the saddle, I think I'll put on the steel caps. Because all this stuff is really bloody heavy. Being a boxway machine, it needs 3 gibs. This is a guiding way on the inside here. Obviously the 2 top flatways. There's a gib down in here which sets the horizontal movement, and then there are 2 gibs which grip underneath the bed to control the vertical movement. Luckily, when I pulled it apart, I bagged and tagged everything so I know how it goes back together. One disadvantage of a boxway lathe anywhere along this surface is going to translate 1-to-1 onto diameter changes, but this specific lathe is in pretty nice condition. When I first got it, I only measured 11 microns thickness variation from the most worn point out to the very end of the bed. And you do notice this, like it's now a little bit tighter here at the end of the bed. And in this portion of the bed, it feels smoother. It feels like the gib is adjusted about right now to be able to get all the way to the end of the bed. So I'll put a clock on this and we'll see what that means in terms of movement in the loosest portion. Right, so this is a 1 micron clock. Now pushing away. That's pretty thick whey oil I'm using. It's 220 weight. For doing these measurements, it would probably be better to use a thinner whey oil, but still, you can see sort of maximum movement of about 5 microns or so. These saddle gib block mount bolts are 12.9. So the 12 means it's got a 1200 newtons per square millimeter tensile strength, and the 9 is a multiplier. So 90% of that, 1080 newtons per square millimeter, is the yield strength. And looking on the chart, the maximum torque should be about 45 newton meters. The Z ball screw gets these expanding spring steel covers. They need to have sockets to go into. Probably going to be easier to install these if I compress them first. Hey, you know last week how I pointed out a couple of channels that I found? Jeremy Makes Things and Drills, Taps and Dies. The YouTube algorithm showed me another really cool new up-and-coming channel. It's a Kiwi guy. The channel's called Odds and Ends Machining. You can see the influence of Alan Milliard in his channel because he's also making his own little twin-cylinder motorbike. Whenever anybody casts their own crankcase for a motorbike, it's got to be worth watching, huh? So go and check it out. Odds and Ends Machining. There should be a link up the top here. Whoops, that's no good. I can't rotate the ball nut. I'll have to watch the old videos to see how the spaces go. Oh, bugger. That's a shaft seal. Oops, I guess I should have bought a new one of them. I took the day off work today, so maybe I can go and get a replacement. Well, one of the nice things about living in a city, you can normally find a supplier of that sort of thing. Mail time. Aha! Pneumatic couplers. Great. And a 50mm shell mill. I guess the shank's coming with a different package. Alright, let's just pack these Z-axis bearings. You know, I've got two different versions of the manual, one hard copy and one scan, and yet neither of them actually show my drive configuration. The hard copy shows a gear-driven ball screw, whereas the scan that I've got shows a belt-driven one, but with the bearings on the opposite side. So Schaublin must have taken 3 shots at designing this. Luckily, the seal and bearing spaces on mine match that gear-driven design. Yeah, that seal surface obviously is here, so I need to drop it all out again. Now I could bash this seal in, but I'm not a big fan of bashing precision parts. You know, I found this piece of scrap that's very close to the right size to press in that seal. So let me just quickly modify it on the lathe. You know, I find it interesting how different manufacturers come up with different solutions for very similar problems. Like, for example, I was looking at an aircraft engine this week, it was a Honeywell, and I noticed that the lubrication pump system is a pretty classic sort of sand casting by the looks of it, whereas the fuel control unit on the same engine is obviously just milled out of a billet with a 5+ XC milling machine. Now I'd speculate that the fuel metering unit's got much closer tolerance bores and valves etc. inside it, and probably more of them than the lube unit, and that probably explains the difference in design decisions. Okay, that existing shoulder is 44, that's about the right size, slightly under 45. Given how the bearings behind here were completely filled with varnished coolant, I'm not exactly sure how effective the seal here is. Runs on that surface there. Now, although these are P5 bearings, they came out as just a pretty easy sliding fit, so they should go in just as easily. And there were no marks between the two bearings. I would have expected some sort of a marking, but there is none. I guess it's not a high-speed bearing. The ground inner race spacer and the outer race spacer. A very gentle tap. There we go. Hey, I've got a couple of questions for you guys. The third screw, the one that goes in here, why was it not in the bag with the other screws? And the second question is, where is it? The ball screw is driven by this pulley, and this pulley has a clutch mechanism to its hub. I guess in case you crash the machine, just it slips. So this plunger fits into the detent, and there's three of them of course, goes in those holes. Plunger is spring loaded. Now what I don't know is whether the ball goes against the pressure plate or whether the ball is inside the plunger by the spring. To me it would seem logical to put the ball on the back of the spring against the pressure plate. However, when I looked through my old videos of pulling the mechanism apart, it didn't look like that. It looked like the ball was inside. I think these balls only became visible in the ultrasonic cleaner. So I think it goes like that. I'll assemble it like this, but if anyone has any experience, I'd appreciate it. We do have the diagram here. It definitely doesn't show the ball between the spring and the pressure plate, although hard to tell if the ball's at the other end of the plunger. There's a mark on this side from the key, so that must be the inside. At this point I ran out of hands to install this, so I had to wait till our number one fan Nico popped round the other day. In the meantime, there were other things to get on with. Right, now I've got new fittings, I can fix this. Got one of those assortment bags from Amazon with 4 different sizes. Now they're not original Festo. This is quite an easily accessible area, so it doesn't really matter if they leak or don't work, because it's easy enough to get back in and fix them with proper ones, if that's necessary. Well, that's better. I'm tempted to put a 90-degree join in the second pipe as well, but since it's not had any problem until now, there's probably no point fixing something that's not broken. Huh? So here's the anti-rotation feature here that stops the collet closer air system from rotating. Now I thought it engaged with this notch here, but it doesn't. Now looking here, it shows a block with a screw from the bottom and then some sort of a pin going out. So this block here is adjustable forward to back, but it's already extended as far as possible and it's not engaging properly. So I'm wondering whether I'm missing some part or this is just, I don't know. Well, I reached out to Jürgen and Lawrence, who have the same lathe, and you got back to me with this photo. So it looks like the anti-rotation feature has just snapped off, and I'll have to remanufacture it. Now these are the bolts to mount that cover, and this one is 70mm long. So I'm guessing I somehow got confused, because this one I'm pretty sure is the one I need down here. And even if not, it's going to be a lot easier to replace that screw on the cover. Right, cheater bar on the Allen key just to stop it turning. Right, that's tight. Right, that's the ball screw installed. Next up, let's hang the motor. Just need the pulley on here. I really like threaded hole into the key, so it's easy to remove. You can just use it as a puller. And I wish everyone did that with keys. Because I'm recycling the original pulleys, what I got is a 5/8 of a hole here and a 19mm shaft. Two options, either I drill out the bore or I turn down the shaft. Once you take the clamping collar off, the shaft's got an outer diameter of 22. If I turn this down, I'll end up with a 1.5mm wall thickness. On one of the German forums, I know one of the guys did this, turned the bore out to 19mm and hasn't had a problem with it. So I think that's what I'm going to do. Now these are 17 toothed, so there's no easy way to clamp them. Like you can't clamp it in a 3-jaw. I guess you could clamp it in a 4-jaw and just move it around. But I think the easiest way to do this will be to turn up a lost collet in the 3-jaw chuck, and I'll use that same slug of aluminium to make up a clamping collet to hold it concentric. And the target dimension for that collet is going to be about 26.3mm. Now that that's cleaned up, I'll go to jaw number 1 and just put a pop in there so I know when I take it out how it lines back up. To get most of the metal out, I've got a 1-inch drill. Right, need to go into back gear. So pretty much spot on 26, need to take 3/10 off. Okay, that looks pretty close. The last thing I'll do in the lathe is just put a little ring on it, just so I know where to drill. Right, I'll just use my other chuck to eyeball the dividing. It's not that critical. That's going to be the top jaw, so I'm going to want a slit here, hole here, and a hole here. Right, now cut the flexures and it's ready. That should hopefully clamp with almost no run out in the chuck which it was made in. And here's the moment of truth. I'll put a clock on it to see if it actually does run. Well, it was a nice idea, but it didn't work because I've got 3/1000 of an inch run out there, which is too much. So I guess I'll just use this collet in a 4-jaw chuck and dial it in. So guys, tell me in the comments section what I would have to do differently to make a collet like that actually run the concentricity. Is it just me, or are chuck jaws always in the wrong alignment for the next job? That's why I've got 2 nearly identical 3-jaw chucks, so that I can have one always with its outside jaws fitted and the other always with its inside jaws fitted. Right, a bit of fluffing around and I think I've got it now pretty much as good as I can get it. Pretty close to 0 run out. Now my normal boring bar is a little bit too large to start in a hole that small. Luckily I've got this little carbide boring bar for the opposite side, but that's okay. I'll have to run the chuck in reverse, but also here I'll be taking such light cuts I've got no real worry about the chuck unscrewing. I have put this collar just on loosely, just to stop any deflection of those petals from expanding out. I won't crank that down because that would distort the size of it. Now I'm going to need a bed stop because I need to go in about 31mm, 30.8 actually. I think what I'll do is use the T-nut under the bed and just put in a T-nut and bolt down a hard stop. I found just the right block in my clamping set. And it clears the chuck drawers. Right, now I've set the tool against the work. So that's my 0 setting. Now this is one of those areas where gauge blocks come in handy. So if I take a 23.5 and a 1.3 plus I guess what a 6. Yeah, that gives my 30.8. So with my gauge block stack here, just push my stop block up against them, clamp that down. .35 to go. I'll do a cut of 20 and a cut of 15. And here's 9 to go. I will need a little bit of clearance, so probably go another 11 or 12. Okay, looks like I've gone 3 over. I was aiming for 2 1/100ths over, so that's not too bad for boring. With snap gauges you always have to take multiple measurements because it's not the most repeatable instrument in the world. Yeah, that's also showing about 3.5, 4 over. Right, well that was actually the shorter X-axis drive pulley. Right, and now with the longer one, it's just rinse and repeat. Well, it did the same job on the second one, it's done. So, and the fit. Seems pretty good. As the new shaft is much shorter than the old shaft, as I saw on the German machining forum, I made up a shaft extension which goes on there. Now, I don't know if this really makes much difference, but it certainly doesn't hurt, so just put that in. So after all that, what sort of runout do I end up with? Okay, that's 1/1000 of an inch. 1.5. Looks like I end up with about 1.5 thou of run out on this one. Now checking the run out on the Z motor pulley. That looks about the high spot there. And once again on this pulley I also seem to have about 1.5 thousandth of a banana run out. Now I really don't know what the design tolerance is on a belt like that, but I just have to take what I get, I guess. Right, a nice gentleman at a local bearing shop, Ibex Bearings I think they're called, helped me out to find a set of seal, so I'm ready to get this oil tank back together. The oil tank is the apron on this lathe, and it also mounts the ball nut. First off, a metering ball, then a spring, then the big main pump return spring. Then on the other side, ball. Oh wait, I missed the washer. So this little cap, it uses an 11mm wrench. I mean, come on guys, who designs things with 11mm wrenches? Nobody uses these things, huh? Now I want to test that this pump actually works before I reinstall it all, so let's... Nope, so far nothing. Darn. I wonder whether I needed to prime it before I put the pump in, or whether I've put it together wrong. I mean, it's not exactly complicated. It's got ball, spring, washer, spring. Yeah, once again, ball, spring, and then that end fitting. I mean, it sure feels like it's just empty and doesn't self-prime. Well, I was hoping it would self-prime overnight, but it obviously doesn't leak that much. Let's try priming it. Alright, now it's working. Brilliant. Before I torque it up, another quick oiling check. These screws go through ribs in the oil tank and secure the ball nut. Oh darn, the gib has got a capture feature on it, which means it has to go onto the tank before the tank gets mounted. So I have to take it back off again. I shouldn't need to drop it down completely, that should hopefully be enough. Okay, with that now in place, I can bring this back up. I'm not sure if you guys like the sound of torque wrenches as much as I do, but it's a very nice sound, I think. Well, this is another big step closer to actually getting motion. I'm pretty happy with how that's gone. Well, there we have it. The mechanicals of the Z-axis drive system are now completely installed. I guess I had hoped to get more done, but as always, things take longer than expected. But next week, the big challenge will be trying to get some power onto this motor. Thanks a lot for watching. And if you're enjoying this series, maybe consider sharing a link to somebody else who might like it as well. Thanks a lot. I appreciate it. See you next time.